At this point, I want to introduce a new notation, and this notation is going to help us figure out how to solve these differential equations in a way that is going to make the algebra a little bit easier. So the differential equations part's still going to be a little bit new, but the algebra will be easier. And what I'm going to do is I'm going to introduce the notation for a derivative in a slightly different way. So I'm going to say dy is y prime. And so really what's happening is that d is a linear operator. This is linear in the sense of linear algebra. You can think about it as a linear operating acting on all of the differentiable functions, which turns out to be a vector space. And so you could think of d as just the derivative operator. So what that means is that if you see dy, that means take the derivative of y. And if you were to compute d of dy, on the one hand, we would call that, because it's a linear operator, we call that d squared y. This just says take the derivative of whatever this dy is, which is y prime. So in other words, take two derivatives. So d squared y says take two derivatives. Likewise, d cubed y says take three derivatives, and so on. And so what I want to do is I want to solve a differential equation using this notation. So let's solve where we have, I'm just going to do this so that you can kind of see how this works, but we're going to have d squared minus 4d minus 12 all times y equals 0. And so this is a differential equation just written in this differential operator form. And so what this says is that this is going to be d squared y minus 4dy minus 12y. And I should tell you that when I have a constant times dy, this is just a constant times y prime. So constants can come in and out of linear operators as much as you want. Basically, you know how derivatives work. You can bring the constant in and out of a derivative as much as you like. So that's what we can do with those. So this tells us that, well, d squared y is the second derivative. 4 times dy is 4 times y prime minus 12y equals 0. So this is really, when you write it like this is actually a differential equation just using differential operator form rather than actually thinking about it in terms of derivatives. The advantage to doing that is that if you're going to solve this differential equation, what you have to do is you have to think about what's the characteristic equation that we're going to look at. So we're going to look at r squared minus 4r minus 12 equals 0. And notice that that's exactly the thing that we had here, except instead of the differential operator d, you have r. It's a quadratic equation in r. And then it turns out that your solutions are going to be, let's see, this is going to be, so this implies that r minus 6 times r plus 2. Did I do that right? Minus 6. Yeah, minus 6 plus 2 is equal to 0. So your solutions are going to be 6 and negative 2. And therefore, your general solution to the differential equation that we started with is going to be c1 e to the 6x plus c2 e to the negative 2x. But this differential equation, this notation, I should say, this differential operator notation just saves us. We know that we can just replace all the d's with r's and look at that equation. So this saves us from having to factor as much as we need to. So let's do one more, and let's do it without actually having to write down what the actual notation is. But let's solve d times d minus 3 times d plus 1 y equals 0. Now, when I write it like this, I need to be, again, a little bit careful about what I mean here. When I write d plus 1 y, what I mean is dy plus 1y. So dy plus y. And so that's y prime plus y. And likewise, d minus 3y. So if you were to do the same for d minus 3y, that would be dy minus 3y. So y prime minus 3y, and so on. But the advantage is that now I can give you this differential equation in this form. And what we have to do is we have to look at what's r times r minus 3 times r plus 1. When's that equal to 0? And of course, that's equal to 0 when r is 0, 3, and negative 1. And so the advantage of using this differential operator form is that it actually makes the algebra of solving these differential equations easier. And so our solutions to this cubic equation is going to be 0, 3, and negative 1. And therefore, our general solution to this differential equation would be c1 e to the 0x, which is just c1, plus c2 e to the 3x, plus c4 e to the negative 1x. And therefore, we don't have to actually think about what is this cubic equation. I mean, you could, if you want, you could multiply all of these together, figure out what that is. And it turns out, I think let's just do that just one time. If you were to multiply all of these out, you would end up with d cubed minus 2d squared minus, let's see, what would that be? Minus 2d, no, minus 3d, all times y equals 0. So in other words, you'd be looking at the differential equation y triple prime minus 2y double prime minus 3y prime equals 0. And then you'd have to figure out what's the corresponding characteristic equation. How does that factor? Well, it factors nicely here. So that saves us that step of having a factor there. Okay, but this is going to be a nice method that we can use to talk about more complicated differential equations without having to factor 8th degree equations. Okay, so this will be very nice for us.